Hi, Ms. Zimmer here, and we're going to start with tangents, section 12.1. Well, first, a tangent can be a line, it can be a ray, or it can be a segment. The key to being a tangent is that it hits a circle at only one point. We call that the point of tangency. Now, if our tangent is a line, like it is here, it would be line AB. If we, let's say, didn't have that second arrow, we might say it was ray BA. Or if it didn't have the line here, we could say B, but we don't have another point. So this is the easiest one to call it, BA. Or we could name it a segment. We could also have a segment BA or AB. All of those would be considered a tangent because they touch a circle at only one point outside the circle. You can't have a line, segment, or ray touching a circle at one point inside the circle. It's not possible. It has to just barely hit it on the outside. Now, one of the first theorems, and by the way, I am using the notes that I did put in your materials folder. So if you haven't printed up 12.1, you may want to print it up, or you may want to look at that and read through it as you go along or after, so that you can see, it's color pictures, it's a little bit easier to read. I'm sort of boiling it down and summarizing it here on the board. Now, the first theorem about a tangent and a radius. If we draw a radius to the point of tangency, remember point of tangency, that one point where a line, ray, or segment meet the circle, then we automatically have a right angle. In fact, we have two because it's a right angle on both sides. Now, how is that going to help? Well, let's look at this example down here. If we're looking for x, we have two tangents in this picture. We have segment LM that is a tangent, and we have a segment NM that is a tangent. And both of those are perpendicular to the radius, NM being perpendicular to NO, and LM being perpendicular to LO. So knowing from our previous section that this is a quadrilateral here, and quadrilaterals have 360 degrees, we already have 290 degrees, which is 180, and that leaves 180. And if we subtract 117 from that, then we'll get 63 degrees. And that 60 degrees is what is left over for angle X, 63. So automatically, these are supplementary if those are both right angles. Okay, moving on to another problem. Now, if a tangent or a right angle is already present, that leads us to some situations where we can use the Pythagorean theorem that we just used in our last chapter. So that Pythagorean theorem just keeps coming back. So one of those circumstances, if we have a tangent and we also have a radius and another segment that connects that up, well, we know, okay, there's a right angle here. In this particular problem, we have to find x, and these are the values that are given. Now, if we know that there's a right angle here and it's a right triangle, then we take the legs, the x value and the 12 value in the Pythagorean theorem, and we square them and add them. And we set that equal to our hypotenuse. Now, our hypotenuse is not x, that's a radius. It's not 8, that's only the section or segment outside of the circle. So this whole hypotenuse is x plus 8, which means we have to use a little bit of algebra. Sorry for putting the square there. This is x plus 8 squared. So this is your a squared, your b squared, This is your c squared, or your hypotenuse x plus 8 squared. Now, a little bit of reminder from Algebra 1. This x plus 8 squared is x plus 8 times x plus 8. So we have to FOIL it. Remember, first, outer, inner, last? First, x squared, outer, 8x, inner, 8x, and last, 64. So if we combine these middle terms and we rewrite this, we've got x squared plus, we'll go ahead and turn 12 squared into 144, and then we'll copy over here, x squared plus 16x plus 64. So we've used our FOIL, and we've combined our middle like terms. So that's where we get this trinomial from x plus 8. Be careful, sometimes people will say x squared, and they'll say 8 squared, and they'll forget that in FOILing you have outer and inner terms that have to be multiplied as well. Now the good news here is that you have x squared on both sides. So really it cancels out, so there's no factoring or any other special circumstances needed. And if we leave the 16x here and we subtract 64, we get 80. And then we find out that 16 goes into 80 5 times. Yes. And so x is 5, which will make sense, because if this is 5 and this is 13, does 5 squared plus 12 squared equal 13 squared? And yes, it does. 25 plus 144 is equal to 13 squared, which is 169. So big check, that works. So you're going to see several problems with the Pythagorean theorem in this section. Now, another Pythagorean theorem problem is actually working in the reverse. They're actually giving you all of the sides, and they're asking you, is that a right angle? Is this a tangent outside? So let's take a look at that. So just because it looks like a tangent, you can't say that it is until you prove it. So given a 7, a 25 here, and a 24 over here, you can't say, well, this has got to be a tangent. It's only hitting the circle at one point. The question is actually saying, is ML, is it a tangent? Is it a tangent? So we're going to go ahead and prove it by just taking those values, the 7 and the 24, plugging in those for A and B, plug in 25 for C, and then square it. If it's equal, it is a right angle and a right triangle. If it's not equal, then it's not a right triangle, and then we could say ML is not a tangent. So let's check this one out. 49 plus 576 equals 625. And yes, that is true. Check. So it is a tangent. Yes. ML is a tangent. And I'm sure for my math lab, you'd be checking a yes or no box. And if you check the yes box, you probably are providing this statement, or they're having that statement at the end. Or if it's a no, they would have that this is not true. But since we know it is true, in this case, it would be a yes. All right, a couple of terms that may come up. Common tangents. So if you have two circles, and I'm going to do my best drawing, this is why I love my printed notes. A common tangent would be a line that hits two circles at one point. So they share a common tangent. Can they have two common tangents? Sure. So here we would have two common tangents. Now, it's possible that you could have another common tangent. Let's see, one common tangent, if you have one circle inside the next, just trying to make sure that I draw this correctly. You could have a tangent, one common tangent between two circles, but that would mean that one circle is inside the other one. So that's certainly possible. If circles have no points of intersection, you might have one circle inside the other. You can have circles that are tangent to one another, joining out just one point. So there's a few options there. You could have possibly 4 common tangents. Let me see if I can draw this one exactly right. I will do my best. So let's see if I can do that. And this, get the other circle in there. So, and then another tangent here. So here's a common tangent, there's a common tangent, and here's a 4th common tangent. So it's certainly possible for circles to have no tangents, no intersecting points, nothing. One tangent either between them, here's a tangent line, a tangent point if they have one inside the other, beside one another, or a couple of common tangents in this direction. Okay, so there's several options as far as where tangents are located. They're not really going to put you too far to the test, but they may ask you a couple of questions about common tangents and how many there can be. Now, what's really important is the next theorem. And this one kind of shows up in disguise all over the place. So let's start with the basic theorem. If we have a circle and we have 2 tangents, one tangent, 2 tangents. Well, we were just talking a moment ago about the radius in here, but one thing that's really important is that these 2 tangents, from the tangent point of tangency to the exterior point and the point of tangency to the exterior point, they are congruent. So if we call this A, B, C, AB is congruent to BC. Excuse me, that should be a segment, that's squiggly. Or we can say that AB is equal to BC. They're of the same length. That's going to help a lot with some solving. Now, as I said, some of these problems will be in disguise, but not quite yet. Let me show you one where the algebra might get slightly tricky. Let's say we have our common tangents here, and we're solving for x. X squared is here, and on this side we have 10x minus 9. And we look at that problem and say, okay, well, we know 2 tangents that meet an exterior point, they have segments that are equal, so that means that x squared is equal to 10x minus 9. Well, wait, that x squared is not disappearing, so what do? Walking back again to Algebra 1, if an x squared does not disappear, we move everything on one side of the equation and have 0 on the other. Now, does it matter which side of the equation you move it to? It does. What you have to do is look where the x squared is, and where the x squared is positive, that's where you want it to be. So x squared is positive here. We're going to move the 10x, and we're going to move the 9. Remember, by moving them, you're actually subtracting this one and adding this one. So that's why the signs changed. Just remember, if you switch sides, you switch signs. So now we have a factor problem. So instead of FOILing that we reviewed a moment ago, we're going to be factoring. We're going to reverse the process. Hopefully this all comes back to you. X times x for the first part, And then we need numbers that multiply to 9. And remember, if the sign here is positive, the signs are going to be the same here. And they're both going to be whatever's in the middle. So they're both going to be negative. If this was a negative sign or subtraction sign, then it would be plus minus. They would be addition and subtraction. But this means they're the same, they're both negative. Now, so we need numbers that multiply to 9 and add up to negative 10. Negative 1, negative 9 multiplies to 9 and adds to 10. For example, if you picked 3 and 3, they would multiply to 9, but they would add up to negative 6. So that wouldn't match. So this is the only option. Now, if you recall from Algebra 1, in order to find our x values, we have to set each factor equal to 0. So x minus 1 equals 0, and x minus 9 equal to 0. So x could be 1 or x could be 9. Well, let's check it out. If 1 is squared, we have 1 here. 10 times 1 is 10, minus 9 is 1. So both of these segments would be 1. They would be equal. So that's a valid answer. Well, let's check out 9. 9 squared is 81. 9 times 10 is 90, minus 9 is 81. So that's also a valid answer. So we have 2 possible answers for this one. So in MyMathLab, we would include both 1 separated by comma, 1 and 9. Okay, so the concept of these being equal is not too complicated, but sometimes the algebra can make you stretch a little bit into what you learned last year. All right, now another circumstance, mathematically much easier, but you have to recognize that we're using this theorem still. This is where I said the problem could look like it's in disguise. All right, give me 1 second to make sure that I put this circle in a good spot. I'm going to give it a try on the first. Okay, so not too bad. So let's say we have this picture, a triangle with a circle in it. And the numbers, pardon if it's not exactly to scale, are 10 centimeters here, 15 centimeters, and let's say 6 centimeters. So not too bad. Well, using this principle, if these 2 tangents meet an exterior point here, then that means that this is also 10. And if these 2 tangents meet an exterior point here, that means that this is 6. And if these 2 tangents meet at the exterior point out here, then that means this is 15. Well, there's no x value here, but the question might be something like, what's the perimeter? I probably should have started with that question. But if the question is, what is the perimeter? Now you just have to add everything up. These 2 sides are both 10 or 20, both 15 plus 30, and both of these together are 12. And you can see 20 plus 30 plus 12 would be 62 centimeters for that perimeter of that figure. So it's 3 of these in one picture. So it kind of looks disguised because we're looking for a triangle problem and there's no triangle in this one. Now, this could also have quadrilaterals. It could be 4-sided figures. It could have 5. They could fit a circle into just about anything like this. And they would, again, keep in mind, these would be equal, these would be equal, these would be equal. I'm running out of tick marks. And these would be equal as well. So you can find the perimeter or any missing x value that may present itself. All right, if you need some question and answer help, please let me know. But these are the principles that you will use in your homework for section 12.1. Catch you next time.